7. This week is the equipment week, and we are lucky enough to have Dr. Hickman with us, who's going to be chairing today. So I'm going to hand over to Dr. Hickman.
Thanks. So we hope we're going to have 3 presenters. We've got 2 at the moment. Today is an equipment day. I think you already know the rules of engagement, don't you? Whilst somebody else is presenting, please mute your own microphones. Once the presenters have finished, we'll have time for questions. If you've got a question that you'd like to ask, keep your microphone muted, but use your mouse to raise your hand. I'm going to be muting my own microphone in a bit, and our first task of the afternoon is going to be to see if we can share presentations with Sarah so that she can talk to us about methods of measurement of oxygen and CO2. Dave, are you able to do that, or would you like me to do it? You'll have to unmute yourself first. Are you able to do that, or do you want me to do it? You're going to do that, are you?
Yeah.
Brilliant.
Sorry, Sarah, was
Okay, I'm going to let Sarah proceed with Dave's assistance.
So yeah, O2 and CO2 measurement. Is that on there?
1 second. So you should be able to take control of that, Sarah. There should be a box that says take control.
Where would I find that?
Little grey box. It's usually on the left-hand side.
I'm doing my phone.
Okay, touch your screen, and there should be an option for it.
Bottom bar, and it doesn't say take control on there.
Okay, so you just have to present and tell me next slide when you want next slide, okay?
Sorry about that.
It's okay, there's a slight delay, so don't shout at me too much.
Okay, so yeah, I'm Sarah, and I'm going to be talking about oxygen and carbon dioxide measurement. So next slide, please, Dr. Maria. Yeah, I changed the objective slightly to just read oxygen measurement and carbon dioxide measurement. So I'm not going to go into details of what oxygen is. I'm just going to talk about oxygen, how we measure it, and carbon dioxide and how we measure that. So hopefully by the end of this, you'll know the broad strokes of that. Next slide, please. Okay, so oxygen. So broadly speaking, there's 2 ways of measuring oxygen. So there are electrochemical methods and physical methods, and the methods that I'm going to talk about I've highlighted in bold. So the Polarographic Clark electrode and the galvanic fuel cell, the paramagnetic analyzer and mass spectrometry come under physical methods, and within that there's also Raman spectroscopy and photoacoustic spectroscopy, which I'm not going to talk about because it's going to probably be too much for this presentation, and because I don't fully understand them completely yet. The other things that I'm not going to talk about but are ways of measuring oxygen are using pulse oximeters and transcutaneous electrodes, but I haven't covered pulse oximetry or capnography, so I felt it was more in the monitoring side of things, and again trying to keep presentation below 20 minutes. Next slide please, Dr. Merritt. So the first electrode I'm going to talk about is the Polarographic Clark electrode, if I can get my tongue around that word. So this is a picture of the electrode, and I'm going to try and explain it. So basically what it is that there is a cathode and an anode, and those are 2 electrodes that are immersed in an electrolyte solution. and there are reactions that happen within the electrolyte solution at the anode and the cathode, and it's all to do with electrons and what they're doing. So within this picture, you can see that on the bottom, blood sample is moving across, and there's a plastic membrane. So that plastic membrane is there to provide a barrier between the blood and the electrolyte solution, and it allows diffusion of oxygen across into the electrolyte solutions. That's what's shown. And then there are two electrodes that have reactions going on based on the oxygen. So at the cathode, there's a reduction reaction. And if you remember back to A-level chemistry, oxidation is loss of electrons, so oil, and reduction is gain, so gain of electrons, so oil rig was the mnemonic that we learned at school. So there's a reaction that happens, which I've written down there. So oxygen plus water plus electrons gives you hydroxide ions. So the reaction at the cathode is consuming oxygen, and electrons are gained, and then the hydroxide ions then migrate to the anode, and at this reaction, at this electrode, the reaction is losing electrons, which then react with the oxygen and give you the electrons that then migrate to the cathode, and that reaction keeps going. And within the electrolyte solution, you've got dissociation going on, so you've got generation of chloride ions and hydroxide ions that are then involved in the anode and cathode reaction. So the generation of electrons generates a current, and that current is then measured by the device at the top, and that current is then proportional to the amount of oxygen that is in the sample. So next slide, please. Yeah. So as I said, there is a cathode and an anode, and they're made of two different things. So the Polarographic Clark electrode is made, the cathode is platinum cathode, and that's a way to remember it. And the anode is a silver chloride anode, and the electrolyte solution is potassium chloride. And it measures the partial pressure of oxygen in a blood or a gas sample. And it's the current that's measured, and the current is directly proportional to the partial pressure of oxygen in that sample. There are a couple of things that it's affected by. So it's affected by temperature. It needs to be kept at 37 degrees, and it's affected by pressure. And the plastic membrane is there to prevent or reduce protein deposition on the cathode. And this is important because it will increase your response time. If there is protein deposition, it makes it harder for oxygen to diffuse across. So leading on to that is that the response time for this electrode is slow. So it can be 20 to 30 seconds. It takes a while. And it also needs a polarizing voltage of 0.6 volts applied across it. And it needs replacing every so often. And where you might find it, you'll see it in an arterial blood sample analyzer. So your ABG machine uses the Polarographic Clark electrode. Sorry, I really can't say that word very well. So that's one way of measuring oxygen. And then if we can go to the next slide, talk about the next way. So the next way I'm going to talk about is the galvanic fuel cell. And it's in principle very similar to the Polarographic Clark electrode. And so, but the difference is in what the cathode, the anode, and the electrolyte solution are, and the reaction that's happening is the same, but involving the different metals that are there. So you have a gold cathode, and so galvanic fuel cell has a gold cathode, and that's the way to remember it, and it has a lead anode, which is Pb there, and the electrolyte solution is potassium hydroxide. And what's happening is that oxygen is reduced by electrons at the cathode again, and it produces your hydroxide ions, which again migrate to the anode, and the electrons are then released by the oxidation of the lead anode, and that generates a voltage this time. So it's a voltage that's measured, and again the magnitude of the voltage produced is proportional to the concentration of oxygen. Again, there are things that it's affected by, so temperature has to be kept at 37 degrees. It does experience drift, and has a limited lifespan, and this is something that needs special nitrogen packaging. So the example that was given is that it's on the anaesthetic machine, and you might see in the mornings the ODPs will have unplugged it and left it to calibrate. So it calibrates to air, which is just 21% oxygen, of course, and then it's plugged back in. But if it's left on the shelf for storage, it needs to be sealed in nitrogen so that it doesn't start reacting with the air, because then it will be consumed and therefore no good. But it's a really slow device. It's not ideal for pre-oxygenation or for breath-to-breath analysis. So on your anaesthetic machine, you'll have a lag. It won't be an instantaneous result that it gives you. So I think I've mentioned most of that on my next slide. So just go, yep. So I've talked about most of that on the next slide there. Give you a second to go through that. So yeah, next slide, please, Dr. Merritt. The next type of oxygen measurement device I'm going to talk about is the physical methods. And the first one of that is the paramagnetic analyzers. And I'm going to explain what they are and what they do and how we use them. So paramagnetism is a property where magnetic molecules are attracted towards a magnetic field, and oxygen is a paramagnetic molecule. And this is because it has two unpaired electrons in its outer shell, which is spinning in the same direction. And so it's magnetic and it goes towards a magnetic field. The opposite of this is a diamagnetic molecule, such as nitrogen. So the paramagnetic analyzers use this ability of oxygen to distort a magnetic field, and they use this so that they can detect and measure oxygen. And there's several types that you learn about. Classically, you learn about the dumbbell torsion wire system and the null deflection system. And there is a more modern system, which I'm going to talk through as well, which is the differential pressure transducer system. So next slide, please. So there's these both pictures, I think, of the dumbbell torsion wire system. I couldn't find one of the null deflection, but hopefully it's two different pictures that will help to get this topic or try and explain this concept. So the dumbbell torsion wire system, you can see two spheres, two spheres in green, and those are nitrogen filled, and they are balanced on a wire. And above and below them is magnets, which are generating a magnetic field. So when oxygen enters into this area, the magnetic field attracts the oxygen, and the oxygen bombards into it and therefore displaces the nitrogen-filled balls, so it will cause them to rotate. And then you can see that there's a little red dot, and that's your light source, and the blue thing, I assume, is the mirror. And that's a photocell, which is picking up the amount of rotation, the degree of rotation, or the degree of torque, which is being applied on the nitrogen-filled spheres that are moving. The idea is that the degree of rotation is proportional to the amount of oxygen that's present in the mixture, and then that's converted into a electrical signal, and then that's processed, and it gives you a measure of the oxygen concentration. Building on that is the idea of null deflection, where the glass spheres do not rotate. Instead, they're kept in a resting position by an opposing current that's applied across them. So again, oxygen is introduced into that region, and they're attracted into the magnetic field, and the spheres want to rotate, but the magnitude of the current that's needed to keep the spheres in their resting position is then processed, and you get an output that tells you that the magnitude of the current is proportional to the oxygen concentration in the mixture. So that's how that works. So next slide. So the more modern systems use a differential pressure analysis, and so they use a slightly different way of measuring the oxygen concentration that doesn't rely on nitrogen or photocells. So there are two entry points which you can see. I'm sorry, the picture's not very clear. I took this straight off another PowerPoint and it didn't quite expand properly. But you've got two entry points, and you've got a reference gas entry point, which is usually air, and you've got the measured gas, which is whatever gas mixture you're giving, and they then are introduced into the system that has two arms, and between the two arms there is a differential pressure transducer, and the two arms link at the top, and then the mixture comes out at the sort of the back, and where the two arms are linking, there is an electromagnet that is at that particular point. So as you've got the two gases coming through, a high frequency pulsed magnetic field is applied, and this is applied randomly, and as the magnetic field is applied, the oxygen will be attracted towards the magnetic field again. So depending on how much oxygen there is in each limb, there will be a change of pressure. So in the limb that's got the reference gas, which is normally 21% oxygen, which is air, there'll be less, and the measured gas that you're giving, there will be more. But the reduction in pressure, or the ratio of the two, is then read and converted into a signal, and that is proportional to the oxygen concentration. And it needs to be a high frequency pulsed magnetic field. It needs to be pulsed and it needs to be random, because if it was on all the time, the pressure between the two arms would equalize, and you wouldn't get this differential pressure being measured, so you wouldn't be able, so it wouldn't work. So this is, as you can imagine, really fast. Its response time is really fast, and it can be used for breath-to-breath analysis. So this is, I think, within the exam, I think that this is something that they're like kind of like a hot topic that they're looking at the moment. So I've tried to explain that as well as I know it. So the next thing I'd like to talk about on the next slide, please, is mass spectrometry. So this is another way to measure oxygen, and the principles of this, there are four main things that happen within mass spectrometry. So there's ionization, acceleration, deflection, and detection. So your sample gas is ionized, that means it's turned into charged molecules, and then it's accelerated and spun round a magnet. And the magnet will, because they're charged and they have a charge, a positive or negative charge, they will, depending on the mass charge ratio, they will either, if they're really heavy, because they've got high mass, they won't bend very much, they won't go around the corner very much, and if they are too light, they'll bend too much, and either way they'll crash into the sides of the magnet. But the mass charge that you've selected that you want to detect, if your magnet is fine-tuned to that, it will then allow those ions to pass through the ion gate and end up at the detector and then give you a reading. And then on the right-hand side of the image, I've put this is a quadrupole mass spectrometer, and that uses 4 magnets. So you can hone down on your sample gas, the amount that you want to detect even more, using 4 magnets. So it's a similar principle, and that's the gold standard, which is used in labs more than clinical. So that's it mainly for oxygen measurement. Next, I'd like to go on to carbon dioxide measurement. So next slide, please. Yeah, so the main 2 methods of carbon dioxide measurement, I've again grouped into electrochemical methods and physical methods. So the electrochemical method, I'm going to talk about the Severinghaus electrode, and physical methods, I'll talk about infrared analysis. I haven't really gone into capnography or like the clinical uses of that as much in this presentation. Okay, so next slide, please, Dr. Maria. The Severinghaus electrode, I put that on the left, and on the right is a pH electrode, and they're both the same principle, and the Severinghaus electrode is a modified pH electrode. So if you have a look at the Severinghaus electrode, you'll see that you've got a reading electrode, which is where the pH sensitive glass is, and you've got a silver chloride reference electrode. And below that, you've got a carbon dioxide semi-permeable membrane. So, next slide, please, Dr. Marriott. So you've got your CO2 sample diffusing across the semi-permeable membrane, and the principle of the pH electrode is measurement based on hydrogen ions, and so this one is as well. So it's measuring the CO2 based on the hydrogen ion concentration. So it's all dependent on this reaction that happens, this carbonic acid reaction. So carbon dioxide plus water gives you H2CO3, which then dissociates to give H plus and HCO3 minus. So the carbon dioxide diffuses across and undergoes this reaction, and the resulting H plus concentration is detected by the reading electrode and is then said to be proportional to the carbon dioxide concentration. And then you use the Henderson-Hasselbalch equation to calculate the PCO2. So again, with this electrode, hypothermia affects the sample readings, so it must be maintained at 37 degrees C, and it's also affected by air bubbles or excessive heparin, which makes the sample very acidic, so it gives you a falsely low pH. So on to the next way of measuring the physical methods of measuring carbon dioxide. So infrared absorption spectrophotometry is one way of measuring carbon dioxide, and the principle is that diatomic molecules or multi-atomic molecules such as CO2 and N2O, because of the bond that they've got between two dissimilar atoms, it absorbs infrared radiation and converts that energy into molecular vibration, whereas oxygen and nitrogen, because they're two similar atoms bonded, they won't absorb infrared. So to the right is a graph that shows the absorption versus the wavelength, and the reason is because they will absorb infrared across a range of frequencies, but they do have a characteristic wavelength where they absorb maximally. And so the characteristic wavelength for CO2 I put there is 4.26 micrometers. N2O is 4.5, so they're really quite close. Their peaks are really close, and volatiles have sort of two peaks, one at 3.3 and the other one at 9 to 10 micrometers, but that's not shown on this graph. So the principle of infrared absorption spectrophotometry is that by measuring the proportion of the infrared that's absorbed, you can calculate the partial pressure of the diatomic gas. Next slide, please, Dr. Marriott. So this is a breakdown of what's happening in the infrared sensor. So on the left-hand side, the infrared light source is produced, and it passes through a filter, and that filter is selective to the wavelength that you're trying to, of the gas that you're interested in. And then the beam is then split, and one passes through a reference chamber and the sample chamber. And then so for instance, if we're measuring CO2, the CO2 in the sample chamber will absorb the infrared radiation, and then the emergent beam that's coming out at the infrared detector will be compared, and the output is inversely proportional to the gas concentration. So if you've got a lot of CO2 in the sample chamber, you won't have very much infrared being detected at the detector. So therefore, it knows that if it hasn't got much infrared being detected, then there must be a lot of CO2 in the sample. And then it's calculated, and the value is then inferred. Just in the seminar room. So there are several issues with infrared analyzers. So first of all, the chamber windows are made of a crystal, so either sapphire or bromide, because glass absorbs infrared and therefore it will give you an inaccurate value. And it's also affected by atmospheric pressure changes. There is a concept of collision broadening, which is where the absorption peaks that I showed you on the graph on the 2 slides ago of one gas are broadened because of a collision with another gas. For instance, carbon dioxide and nitrous oxide. Nitrous oxide increases the value for carbon dioxide. So if you've got 70% nitrous in a solution, it said that it increases the carbon dioxide by about 10%. Oxygen decreases the value, but it doesn't absorb infrared. So I'm not entirely sure why. And volatiles don't seem to have an effect, but I think that's because we don't use high enough amounts of volatiles that it would affect your output of CO2. It also needs a water trap because water has a high infrared absorbance. Oh, wrong, sorry, infrared absorbance. So thank you very much for listening. That's the end of my presentation. I hope that that's made sense. It's quite dry going through all the electrodes, but if you have any questions, I'll do my best to answer them.
You've settled them into stunned silence there, Sarah. Can you just remind me what the mnemonic oil rig stands for? Because that wasn't something that I got when I was at school.
Oh, right. So oil rig. So oxidation is loss of electrons and reduction is gain of electrons. So that's a way to remember what's happening in an oxidation reaction and a reduction reaction.
Nice. If, given that we're actually sort of eating up time, if no one's got any questions, I think we'll move on. Dave, presumably these presentations stay available, do they? Because I thought that was a really clear explanation, and I think you'd be well advised to go through those presentations and just pick out, you know, the little sneaky things about proportionality and exactly what's proportional to what, whether it's voltage, whether it's current, whether it's change in pressure or absolute pressure. I think those are the sorts of things that you can get caught out. You know, they like to trip you up within MCQs. But I thought that was a really nice presentation. Thank you. So next up we have Grace, who's sitting there in pole position already, ready to talk to us about ultrasound. And Dave, I think you're going to get the presentation up for us, is that right?
Grace, have you found it on sharing, or do you want me to do it?
Oh, yes.
So I've just moved them around, so it should be there.
Oh wait, no. It's wanting to share stuff on my computer, but I have got it open on my computer.
Okay, you're on a
That's probably easiest then.
Yeah, do that. Perfect.
Can you see it?
Yep.
What are you seeing? Hang on. Are you seeing? I don't want to accidentally show you like all my.
Just all we can see is your presentation, Grace. You just need to put it onto presentation mode. There we go.
It's flashing. Ooh. Sorry, guys. Is it supposed to be flashing?
It's not flashing for us.
Okay, so all right. I'm just gonna. If something funny is happening, will you let me know? So hi everyone, my name's Grace. I am an ITU fellow at the Leicester Royal Infirmary, and I'm going to talk to you about ultrasound today. It is part of the curriculum. The curriculum expects you to know about piezoelectric devices, basic principles of ultrasound, and also the Doppler effect. So we're going to cover all those things today. I thought we'd start with a little quiz, which isn't really going to work if everyone's muted. So I'm just going to read out the questions, pause, and then tell you the answers. So I've got an extended matching question here, which just to kind of whet your appetite for ultrasound. These are all important terms when it comes to ultrasound. The piezoelectric effect. So if you have a think as to what the answer is, and then I'll tell you. So hello. The piezoelectric effect is the phenomenon by which mechanical stress may be induced in specific crystalline substances when a potential difference is applied across them. So this is the sort of thing you might be expected to define in a viva. The speed of sound in the body is approximately 1,540 meters per second at 37 degrees. It varies depending on the density of the tissue, but That's round about where it is in soft tissue. Contrast resolution is the ability of an ultrasound to distinguish between two separate objects with similar echo-reflective properties. So if you imagine two tissues that are next to each other but have similar densities, the ability of the ultrasound to tell the difference between them is contrast resolution. Similarly, spatial resolution is the ability of a probe to tell the difference between two separate objects that are next to each other. And finally, the Doppler effect is the phenomenon by which frequency of emitted sound is altered as it is reflected from a moving object. If anyone's preparing for the Viva, I highly recommend practicing saying some of these things out loud so you don't get tongue-tied if it does come up in your Viva. And then I've made up an MCQ question, again, to whet your appetite, but we'll talk about all of these things. What would be really cool would be if I could actually see everyone and you could say yes, a thumbs up if it was true or not, but I don't think I can. Ultrasound probe uses the properties of a piezoelectric crystal, which generates a pressure wave in a response to an alternating electrical input. That's true. A separate probe is required to transduce a reflected pressure wave from the tissue to form an image. That's not true. It's all in the same probe, but the one probe acts as it emits the sound wave, and it also receives the sound waves that are reflected back. So it has two functions. Piezoelectric crystals are unpredictable because when an electrical stimulus is applied to them, the wavelength produced is not proportional in a linear manner to the electric signal applied. That's false. One of the nice characteristics of piezoelectric crystals is that they're entirely predictable. So if you apply 50 hertz of electricity to them, the wavelength that they produce is in 50 hertz. Ultrasound machines clinically operate in the 1 to 10 megahertz region. That's true. And finally, ultrasound was first used to treat Meniere's disease. That's actually true. Before it was used for diagnostic imaging, ultrasound was used as a therapy, I think in the 30s, to treat things like Meniere's disease and Parkinson's disease. I feel like I'm in a room talking to myself. It's really strange. Right, so ultrasound. Ultrasound is quite a technical topic that we can go into quite a lot of detail about it. I've gone into some detail, but I think if we try to cover absolutely everything on this topic, it'd be a very long presentation. So I've tried to keep it to what you need to know. Ultrasound refers to high frequency sounds that are above the frequency audible to the human ear. So everything above 20 kilohertz is inaudible to the human ear, but in actual clinical practice, the frequency is much, much higher, between 1 and 10 megahertz. And that's actually sounds that can only be produced by humanly made products. I think animals wouldn't be able to hear these frequencies either. It's produced by a vibrating crystal, which is lead ziconate titanate, which is on the ultrasound probe, and the process by which it vibrates is known as the piezoelectric effect. So being able to define the piezoelectric effect is part of the curriculum. Waves that are produced by these crystals are absorbed by the tissue and they pass through the tissues, and as the more tissue they pass through, or the higher density they pass through, the amount of waves that continue sort of reduce, and this term attenuation refers to the loss of sound waves as they pass through tissue, and there's lots of different mechanisms by which they do that, which we'll go into a bit more detail, and then they get reflected back to the probe, and then the probe produces an image. When the sound waves reach a boundary between two different tissues, they are reflected back, and there's different tissues that have different properties, and they each reflect waves back depending on what their density or acoustic impedance are. So I've done a little diagram for those of you that are visual. So that's my diagram of a probe. You've got a crystal that's in the transducer, an electrical signal is applied to it. And then when it's on the skin, the sound waves then pass through the skin into the tissues below it as the electrical stimulus is applied to the crystal. And as they go deeper through the tissues, the sound waves become attenuated. We use gel to decrease skin impedance, and then these sound waves then get reflected back to the receiving transducer in the probe, and it detects them and then formulates an image based on the amount of waves that were sent out and how many waves were sent back, and the amount of time it took for the waves to go and then come back, if that all makes sense. So if you've got a tissue surface, it will reflect back the waves and back to the probe. Lower frequency ultrasound achieves better tissue penetration. So if you think about a sound wave, the frequency is how many times the sine-like wave can occur in 1 second. So if you've got lots of cycles in 1 second, the frequency is high, and if you've got less cycles in 1 second, the frequency is low. And if the frequency is high, that sound wave is passing through tissue quite a lot, so it's more likely to become attenuated more quickly. But because it's passing through the tissue a lot, it's giving the probe much more information about the tissues that it's passing through, so you'll get better resolution with higher frequency. So essentially, whenever you're using an ultrasound, whatever the purpose for it is, you just want a frequency that penetrates the tissue just well enough to get a good resolution. So you might need a higher frequency if you're looking for something deep in the body, and you might need a low frequency if it's just very superficial. I've borrowed some pictures from Nysora to sort of illustrate this, because it's quite nice to see it visually. I've put some numbers here just to give you an idea of how the speed of sound travels through different tissues or different air, like air, for example. So soft tissue, we've already talked about, on average is 1,540 meters per second. It's a bit higher in tissues like the liver. What was it? Don't worry, I can't remember which way it is now. But in air, it's much less. And in bone, it's much more. So that's one of the reasons that ultrasound won't go through bone. It's because the speed of sound is much higher, but also bone has high acoustic impedance, meaning that it's very dense and it won't vibrate very much with sound going through it. Oh, that was not 1 second. I'm just going to adjust that so that you can see the picture properly. So this is a picture from the Nysora website, which illustrates quite nicely what happens to an image with different frequencies. So it's an image looking at the sciatic nerve and the popliteal artery, and you've got 8, 10 and 12, and you can just see how the image is much better with a lower frequency on the left. There's lots of different ways that ultrasound waves can be attenuated. So this picture on the right illustrates what happens when an ultrasound wave hits the surface between 2 different tissues. And say the one on top is low impedance and the one below it is high impedance. A proportion of the sound waves will be reflected, so that's this angle here, but also a proportion will be transmitted, and a proportion of the transmitted ones will be transmitted at a different angle. This is important because it can lead to artifacts. So I don't know if you've ever seen images when people are using ultrasound where you get mirror images in your picture. Equally with reflection, whenever ultrasound waves hit bone, for example, you get this this area of darkness just below it that expands. Scattering is another form of attenuation with ultrasound waves, where whenever the ultrasound waves hit a tissue that isn't smooth but more rough in surface, it can scatter the ultrasound waves, and it can scatter them in such a way that it doesn't actually enable them to return back to the transducer. So these are just all ways by which ultrasound images can be not ideal. Uses for ultrasound. So this is a common exam question. You get asked what would ultrasound be used for. I would classify it into diagnostic, therapeutic uses, and ultrasound. So I'm sure you all know different methods ultrasound can be used. Can be used for vascular access, can be used for diagnostic purposes, looking for blood clots and flow in blood vessels. It can also be used for cardiac output monitoring and esophageal Doppler. And it also has uses in obstetrics for uterine blood flow and also fetal heart rate, or like fetal cardiac diagnostic purposes for fetal cardiac conditions. There's different types of ultrasound scans or modes of ultrasound scans. So we do need to know that the A scan is the A stands for amplitude, and it is essentially a single beam of ultrasound, a single wave ultrasound. We don't use that clinically very much, but if you get asked to give an example, it is used in ophthalmology for measuring the depth of it's used in ophthalmology to look for the depth of the eyeball. I can't think of the medical term right now. B mode is brightness mode. That's what we are familiar with and use clinically most frequently. And M mode is a motion mode, which allows you to see. It's used quite commonly in echocardiography, and it detects movement of tissue interfaces, and it allows you to make measurements as well. So you would use a B mode image, then draw a line across it, and then the ultrasound will show you the movement across that line. The Doppler effect, so that's another part of another requirement for the curriculum. So Doppler effect is, you can best explain it like when you're standing on a street and you can hear an ambulance, and the sound of the ambulance siren changes depending on where the ambulance is. And essentially the definition is that sound waves are transmitted by oscillations of particles in the direction of the wave itself. And if the sound wave is coming towards you, it's shortened, and if the sound wave is going away from you, then it's lengthened. And this can be used clinically to allow measurements of flow. The Doppler equation allows you to calculate the velocity or flow. So it's equal to the speed of the sound wave times the change in frequency divided by 2 times the emitted frequency. The equation also includes a correction factor for the angle that the ultrasound is actually hitting the moving object. So if it's perpendicular, you don't need that correction factor, but if not, you need to include that in the equation. So that's why there's a cosine of the cosine theta refers to the angle of the ultrasound. Hello? Oh, sorry, I could hear something. So this is a picture of a collar Doppler. People quite commonly assume that red means arterial and blue means venous, but that's incorrect. Red refers to the direction of the flow, and red is towards the probe, and blue is away from the probe. And there's an acronym that you can use to help you remember that. But blue away, red towards. One of the applications for this is the esophageal Doppler. There have been exam questions about this, and there's quite a nice article about it in Life in the Fast Lane if you want to read a bit more about it. Esophageal Doppler is used as they call it relatively non-invasive, but it is a probe inside the esophagus as a method of cardiac output monitoring. The Doppler probe is in the mid-esophagus, and it's angled to measure red blood cell velocity in the descending thoracic aorta. And there's a formula that determines what the patient's aortic cross-sectional area is, and it's based on height, age, and weight. And this allows to make some measurements, for example, looking at contractility, stroke volume, stroke distance. Some of the disadvantages of this is it's very user dependent. But so once it's positioned correctly, sorry, someone's knocking on my door. Hang on. Give me 1 minute. Just going to mute myself.
So I can see that Nissa has joined us, and Grace has just got 2 slides left. So we are
really
a
sorry.
little bit short of time, but we should be fine.
I'm back. Sorry, I'm in my front room. So yeah, we're at the end. So I was basically finished. Ooh, yeah. So we've talked about esophageal Doppler. So we've covered today the physics of ultrasound, uses for ultrasound, different modes, and the Doppler effect and its clinical uses. So thank you everybody for your attention. I've included some references that are quite useful. The Nysora article on ultrasound is quite good. And then there's also an article in one of the BJ educations about ultrasound that's quite useful on top of your usual FRCA books.
So thank you, Grace. Does anybody have any burning questions that you haven't already submitted in the chat? No, I can see that nobody's written anything down. Has anybody got anything that they would particularly like to ask? Any hands going up? So Grace, I liked the way that you mapped your presentation to what the curricular requirements are. I thought that was very sensible, and it made it very clear what you need, what people need to know and what they don't need to know. I wonder if it's worth you perhaps annotating the presentation on the on SharePoint, just to indicate which are the correct and which are the incorrect answers on your slide. Yeah. You've just got visions of a whole group of trainees either contacting you to tell you you're wrong, or learning the wrong thing and then blaming then not knowing why they've learned the wrong thing. That's a really nice presentation, thank you. Nissa, are you there?
Yes, hello, can you hear me?
Yes.
Great, okay. I just need to work out how to get my presentation up.
Okay. We've been working on the principle that Dave has been bringing it up and then giving you control of it.
Oh, amazing. Yeah, that sounds like the easiest thing to do.
Are you working on it, Dave?
Working on it. You have an option that says take control, Nissa?
Yes, got it.
There you go.
Thank
Okay,
you.
so everyone except Nissa needs to mute themselves, please.
Okay, cool. So I've put together a few MCQs and then I've done some SBAs at the end, just to try and offer some useful practice, hopefully. So, I mean, I won't read them out because I don't necessarily think that's that helpful. I'll just let you guys read them and give you like a couple of minutes to jot your answers down and then we can go through them.
Just to mention that if everyone puts their answers on the chat, then we can discuss them once the answers are up there.
Oh, these are true false. Sorry, this one is true false. Okay, I think quite a few people have answered, so we'll go through. Okay, so yeah, so concerning capnography, it's a more useful indicator of ventilator disconnection than pulse oximetry. So I think most people said that was true, which is correct. So capnography obviously responds a lot more quickly than the pulse oximeter. If you've had an esophageal intubation or ventilator disconnection. The pulse oximeter, obviously the patient will desaturate eventually, but like they're not going to do that straight away, and actually their saturations will probably remain normal for quite a few minutes, especially if they've been pre-oxygenated beforehand. B is false, so CO2 is absorbed in the infrared region, it's not absorbed in the ultraviolet region. I think everybody got that. C is false. Obviously, a delay of 38 seconds is far too long. So the book actually says that with a side stream analyzer, you do get a slightly longer delay, but that a delay of less than 3.8 seconds is acceptable. D is false, actually. So they have a little bit of stuff about mainstream and side stream analyzers in the book I've got. Basically, the main principle is the mainstream analyzer responds more quickly, but it can only measure one gas. So they have to be calibrated for a specific gas and then used for that. So if you use a side stream analyzer, then that can measure multiple different gases in the mixture simultaneously. So it can measure the volatile agents, carbon dioxide and nitrous oxide. And then the last one, I think everybody got that's true. So because in COPD, sorry, the alveoli are emptying at different rates and the different parts of the lung have different time constants.
Not when I was presenting.
So you have different degrees of airway compliance and resistance, and that causes a slightly sloping trace instead of the square shape that you'll see in people who are healthy and have normal lungs. Okay. So the next one is about oxygen concentration measurement. Cool, okay. So infrared absorption, I think almost everyone has said correctly that that is false. Oxygen doesn't absorb infrared radiation. So only molecules with two differing atoms can absorb infrared radiation. So for example, CO2, because it's got carbon and oxygen in, because oxygen has just got one type of atom in, then it doesn't absorb the infrared. Paramagnetic analyzers are commonly used because oxygen is repelled by the magnetic field. That's false. So oxygen is attracted to the magnetic field because it has unpaired electrons in its outer orbit. So they're then attracted to the magnet. The galvanic or fuel cell analyzer has a slow response time of around 20 seconds and a lifespan of 1 year. That's true. So the fuel cell is a slightly slower responder, and it gets depleted by continuous exposure to oxygen. So they say the lifespan is around 1 year. The fast responding analyzers should be positioned as near the patient as possible. So that's true, although my book says it's a bit controversial, and that generally they say that the fast responding analyzers should be put as close to the patient as possible, and then the slower responding ones can be put on the inspiratory limb. Yeah, but they do say that there's not a huge amount of evidence for that. And paramagnetic analyzers can provide breath-to-breath measurement. So that's true. So some of the older ones tended to be a lot slower, and they could have a response time of up to 1 minute. So they couldn't do breath-to-breath measurement, but the modern ones have a rapid response, so they can. Okay, number 6. Great, okay, most of you have got these as well, actually. So polarographic oxygen electrode can measure oxygen partial pressure in a gas or blood sample. That is true. So they are generally used in the ABG machines, but they can be used on the anaesthetic machines as well. The electrode acts as a battery requiring no power source. That is false for the polarographic electrode. It requires a power source of 700 microvolts. The galvanic fuel cell doesn't require an external power source. Oxygen molecules pass from the sample to the sodium chloride solution across a semi-permeable membrane. That is true. So there's a Teflon semi-permeable membrane, and the molecules pass across that at a rate proportional to their partial pressure. And then that's how the value is determined. And so the electrode can give, the membrane gives the oxygen electrode a lifespan because the membrane can deteriorate or can be perforated. Then obviously it won't give accurate measurements. Uses a silver cathode and a platinum anode, so they've switched them over there. So actually uses a platinum cathode and a silver anode. And the amount of electrical current generated is proportional to the oxygen partial pressure, so that is true. When the oxygen molecules pass across the Teflon membrane, they generate a really small electrical current as the electrons move from the cathode to the anode, and then that is how the value is generated. Yeah, okay, so this is about measuring oxygen in a gas mixture. Okay, so different ways of measuring oxygen in a gas mixture. So fuel cell, that's correct. Obviously, we've already discussed that. That's when the molecules diffuse through the semi-permeable membrane to an electrolyte solution to reach the cathode. That generates a current proportional to the partial pressure of the oxygen in the mixture. So that is true. Ultraviolet absorption, that is false. So this seems to come up quite a bit, just as like odd MCQs. Halothane absorbs ultraviolet radiation, but I think that's the only gas that can be measured by ultraviolet. Mass spectrometry, so yes, that is true. That can be used for the measurement of any gas, which is quite a good one to remember because it separates them according to their molecular weight. Clock oxygen electrode, yeah, obviously clues in the name. So as I mentioned earlier, usually in ABG machines, but can also be used to measure oxygen partial pressure in a gas mixture. And then the last one, infrared absorption, false. As we discussed earlier, oxygen only has molecules of the same type, so it won't absorb the infrared radiation. Okay, and this is single best answer, the rest of them. I've just seen Dr. Marriott's comment in the conversation. Okay, cool. So I think everyone's got that. Yeah, so basically, so a 16 gauge cannula is way too big. So you might think like, oh, 16 gauge, yay, that'll give me really good flow, but you're basically just gonna like risk completely rogering the artery. So I think usually 20 or 22 gauge is what's recommended. So B, the position of the dichrotic notch reflects myocardial contractility. As you all identified, that is false. So the position of the dichrotic notch can give you useful information about the systemic vascular resistance. So if the dichrotic notch is quite late or very low down the slope or even separate to the first slope, then that suggests that they are very vasodilated and may respond to either some filling or some pressors to cause vasoconstriction. If the dichrotic notch is very early on the upstroke, then it suggests they're peripherally quite vasoconstricted. The monitoring system should be capable of responding to a frequency range of 0.5 to 40 Hertz, not 400. As you said, increased damping of the waveform has no effect on the map. That is true. So it lowers the systolic and raises the diastolic pressure, so you have that very sort of flat waveform. But if you were to calculate the map, then it should still be the same. And air bubbles do not produce an underdamped waveform. They produce a damped waveform. Yeah, they produce a damped waveform, sorry, not an underdamped waveform, because of the difference between the compressibility of air compared to the column of water that normally should be there. Okay, this is SBA as well. Okay, so we'll go through this one. So C is the right answer, which all of you said. So a clot will cause damping, basically, so low systolic and high diastolic pressure. A transducer diaphragm with a very low compliance has a high resistance, so essentially it's really, really rigid. So that will cause the system to be overdamped. So you would have a high systolic and a low diastolic pressure. A soft wide lumen catheter causes low systolic and high diastolic pressures. That is true because basically it causes damping. An air bubble causes low systolic and diastolic pressures. That is false. So again, an air bubble will cause damping. So that would cause low systolic and high diastolic pressures, not low on both. And a long catheter with a wide lumen is ideal. So maximum catheter length that they recommend is ideally 2 meters. You don't want the catheter to be too long. Damping will narrow the pulse pressure. Yeah, because it causes a low systolic and a high diastolic, so it will narrow the pulse pressure. Have I put an error on there? Oh, sorry. No, I might have said something wrong. I'm in the middle of night, so I could well have said something wrong. I agree, damping will narrow the pulse pressure.
Yeah, sorry, I was just going to ask you about damping. We've got, just to make everybody aware, damping is a phenomenon whereby, as you all know, the pulse waveform becomes narrower and flatter. And so air bubbles in the system tend to result in underdamping, where you get a really spiky trace. Clots give you overdamping, where you get a really flat trace. So yeah, I think there's just a little bit of confusion there.
Oh, sorry.
Yeah, and as Alex says, damping narrows pulse pressure. Okay. Everyone all right with that? Yeah.
Okay, so just an SBA about nerve stimulators. Cool. Okay, so again, I think pretty much everyone's got that right. Oh, sorry. Yeah. So the needles don't have sharp tips. So a sharp tip would be more dangerous because you'd be more likely to cause damage to the nerves. And a sharp needle would pass through the different tissue layers more easily, so you wouldn't get as much feedback because you wouldn't be able to feel as much what was happening. Whereas the idea of a blunt needle is it provides a bit more feedback about what you're going through, basically. So AC current is not used to locate the nerves. You use DC current, and by avoiding AC current, the idea is that patient safety is improved. A current of 1 amp would be much higher than what's needed. So usually the current range is up to 5 milliamps. And you could use sort of 0.25 to 0.5 milliamps to stimulate the nerves. If you used a very high current, then the tip of the needle could still be quite far away from the nerve, but could potentially still cause stimulation of the nerve fibers. So then you would not be as close to the nerve as you thought, and your block probably wouldn't work. I agree, paresthesia is not required for successful blocks. Paresthesia implies that the needle is touching the nerve and is therefore probably too close to the nerve. And the idea of the nerve stimulators is you can stimulate the nerve without being in direct contact with it. So you're supposed to get an idea of how close you are to the nerve. And the frequency should be about 1 to 2 hertz, not 50 hertz. If you used 50 hertz frequency, that would probably be quite uncomfortable for the patient, because obviously a lot of these blocks are done on awake people. Okay, this is the last one. Okay, cool. So bag and bottle ventilator, the fresh gas flow is also the driving gas. So that's false. With the bag and bottle ventilator, the driving gas is separate from the fresh gas flow. And there's no mixing between the driving gas and the fresh gas flow. So the volume of driving gas going into the chamber is equal to the tidal volume. B is a minute volume divider. No, that's not true either. So the tidal volume and respiratory rate can be adjusted separately in a bag and bottle ventilator. C, the bellows can be either ascending or descending. Yep, so everybody got that. So I think most of the ones we're probably used to have ascending bellows. And the point of that is that that adds to the safety, because the bellows will collapse if there's a leak, which I'm sure everyone is familiar with and has seen before. The problem with the descending bellows is that they may have almost normal movement if there is a leak, and so it's much more difficult to see visually if you've got a leak. D, with a leak, the ascending bellows may continue to move almost normally. Yep, I've just said that. And E can only be used for adult patients. Obviously, that's false. Can be used for both adults and children, and you can get different size bellows for different age groups if you want to. And that's it. I have no more to offer.
Nissa, that was really good. Does anyone have any questions for Nissa? Or are your heads?
I really hope not, I'm going to be honest.
I have to admit, I sort of sat back a bit because I thought, I can't remember. I don't know. There was one thing about the Polarographic electrode. I noticed that lots of people got that stem wrong, the same one about the electrolyte solution.
Yeah.
That's in a Polarographic electrode. Your stem said that it was an electrolyte, sodium chloride. I suspect the reason why everybody got that wrong was because we've just heard Sarah talk to us about Polarographic oxygen analysers, and I did just Google it quickly, and I think it's actually not sodium chloride.
Sorry.
No, that's fine. You know what, you've done loads of research, so I'm going back. This is quite an old article, but it is by Jeremy Langton, who is a son of Leicester, and he says it's a potassium chloride or potassium bromide electrolyte solution.
Okay, sorry, I thought you could use sodium or potassium, to be honest, but
you may well be right.
I think it's tricky because it depends what sources you're using as well.
If you come across this question, you might want to omit it or plump for it. Mind you, there's no negative marking these days, is there? So it doesn't matter.
There isn't.
Yeah,
I agree. I have read that you can use potassium, but I thought you could use sodium chloride as well.
It was just I looked at everybody's answers, and pretty much everybody got that one wrong. And I suspect it for that reason. Anyway, so you've been reading 2 different books. Not a good question to go into the exam, but a great question to stimulate some conversation and discussion. So thank you.
Cool, thank you very much.
If nobody else has got any questions, I presume you've somebody taken a register? Has somebody taken a register? Was I meant to have taken a register?
No, don't worry. We have a record of who
It's
attended.
automatically done. Don't worry. It registers who's been here.
I've done some, during lockdown, I've done some quizzes using Kahoot, which has been quite good fun. And I don't know, it's a little bit more work sometimes, but once you know how to do it, it's actually really easy. And that might be a bit of fun if you wanted to do that sometime. Just a thought. It's quite easy to do. Even I can do it.
We were using Kahoot at the beginning, I think.
Oh, were you?
Yeah. When we were
Well, you need 2 devices for that, don't you, really? Yeah,
yeah,
don't need to bother then. Right, well, I'm going to say goodbye and thank you for having me.
Yeah, thank you so much, Dr. Hickman, for helping us today. And we really appreciate it. And thank you to all the speakers as well. I've put the feedback link in the chat, so please fill it out. It's really useful. And I can forward that to the speakers as well. It's really useful for them. And yeah,
well done to everybody who has made some really good preparation there. Thank you. And good luck.
Great. Thank you all.
thanks.